Hello, it's Dr. Daystorms again, and this lecture here is one of the most important that we've gone over so far, if not the most important so far of the semester. We're going to go over uncertainty measurement, how to determine the number of significant figures and whether a digit is significant or not, and then finally go over dimensional analysis, which is perhaps one of the greatest skills that you need to master in general chemistry, because you're going to need it throughout all of chemistry. Okay, first of all, let's just go with the uncertainty and measurement. You can imagine that there are different measuring devices have different uses and different degrees of accuracy. So for example, if you have a really large graduated cylinder, let's say a 1 liter graduated cylinder, it may only be accurate to within 5 milliliters, whereas a 10 milliliter graduated cylinder could be accurate within 0.1 milliliters. Okay, and moreover, if you're making various solutions, say for example, you need to first make a solution in a volumetric flask, then you pour part of that into your graduated cylinder, you have some air in the volumetric flask, you've got another degree of air in the graduated cylinder, and then you use a pipette to pipette more of it from the graduated cylinder into the actual tube or whatever that you're going to be using. You have error at each step, and so we have to have some way in order to rationalize and to measure the amount of error that we are encountering. Significant figures refers to actually the number of digits that have been measured. Okay, it helps give an idea on how accurate or precise the measurements are. So what makes something significant? We're going to go over the rules and I'll give you examples as we go along the way. When you round calculated numbers, we have to pay attention to significant figures so we don't overstate the accuracy of our answers. We are limited. There is a limited accuracy to anything as we do math and mathematical calculations. Okay. First off, all non-zero digits are always significant. So if it's a 1, 2, 3, 4, 5, 6, 7, 8, or a 9, it's always significant. If it's a 0 between two significant figures, then the 0 is also significant. So for example, the number 1503 has 4 significant digits, or figures, sig figs. Some people call them sig digs for significant digits. I'll probably say sig fig, because we have 1, 2, 3, 4. This 0 is significant. Zeros at the beginning of a number are never significant. So what's an example of that? 0.00102 grams, for example. Let's see. These 3 zeros are not significant. This 0 is, because it's between the 1 and the 2. So for that term, there are 3 significant figures. Those first 3 zeros were not significant whatsoever. A 0 at the end of a number is significant if there's a decimal point written in that number. So let me give you some examples here. If we say this, 120.03, all of these zeros are significant because of 2 reasons. Well, one reason is because we've got a 2 and a 3 that's significant, so these are the middle zeros. That's easy. What if it was this? 120.0. How many significant figures are there? Since there is a decimal point, Both of these zeros are significant, so there are 4 significant figures. What if it was this? 1200. How many significant figures are there? This is an instance when these two zeros are not significant. There are only 2 significant figures because there's not a decimal point. You'd have to have a decimal point after that last zero in order for those zeros to be significant. So let's start to utilize this in some calculations. Whenever you add or subtract, the answers are rounded to the least significant decimal place. So let me just give an example here. We have 12 plus 8.2 plus 1.35. So we add these all up, 10, 11, carry the 1, 21.55. However, now we have to say what was the least significant decimal place. If we do that, whoops, let me undo that one. If we do that, look here. This first one, the least significant decimal place, is in the ones position. So then we have to look here. We have 21.55. So therefore, our final answer, if we go to the correct number of significant figures, would be 22. Because since it's a 5, it's going to round up to 22. Let's do another example. 1.253 minus 0.01. Okay, so if we do this, you're going to get 1.243. But once again, we need to go to the least significant number of decimal points. And here it's in the 100th position. So therefore, our final answer, according to the significant figures, would be 1.24. Because that 3 would round down to 4, since it's less than 5. 5 or above, you round up. 4 below, you round down. When you multiply or divide, your answers are rounded to the number of digits that corresponds to the least number of significant figures in any of the numbers used in the calculation. So what does that mean? Let's just do some examples. So if we have here, let's see, let me get out my trusty calculator. Okay, let's say that we have this number, 2.35 times 13,000. Okay, 2.35 times 13,000 equals 30,550. Now we've got to put our answer in the correct number of significant figures. So this is actually more simple than what you may think. I always thought that multiplying and dividing was easier. This one has 3 significant figures, the 2, the 3, and the 5. This number only has 2, because these 3 zeros are not significant since there's no decimal point. So therefore, we have to have a total of only 2 significant figures in the final answer. So since that's going to be these 2, you look at this number, it's a 5, so we're going to round up. So the answer is going to be 31,000. Or another way to do it is in exponentials. It's 3.1 times 10 to the power 1, 2, 3, 4. So either one of these answers would be acceptable to me. 31,000 or 3.1 times 10 to the power 4. Let's do another example. $1.000 5 times 6.03, divide that by 0.012 equals. So first, let's enter it into the trusty calculator. Make sure you bring your calculators to class. 1.005. I'm sorry, I've already made a mistake. 1.0005 times 6.03. Divide that by 0.012. And I get this number, 502.75, and it goes on and on and on. Obviously, that's way too many significant figures. So once again, we have to look and see, since we're multiplying and dividing, this first number here is 1, 2, 3, 4, 5, because all zeros are significant, so that one's got 5 significant figures. This one has 3 significant figures. This one only has 2, because these zeros are on the left-hand side. They start the number. So that means our final answer here would have to have 2. So if we're going to be precise, it's 500, but that would only have one significant figure, so we can even say it's 5.0 times 10 to the power 2. 1, 2. See, that's where you get times 10 to the power 2. So that would be the answer to the correct number of significant figures. I've already used these terms, and many times accuracy and precision gets used interchangeably, but that's actually incorrect. First up, accuracy actually refers to the proximity of the measure to the true value. So if you imagine a dartboard, which is what that's attempting to do. We have our dartboard. There's the bullseye. And we've got some different so we have 3 different points in each of these colors. Which of these colors is more accurate? Well, here, the more accurate, the one that has a higher degree of accuracy is the one that's closest overall to the bullseye. And so you'd actually have to measure the bullseye and see which one, in general, would be the most accurate. If we were looking, my drawing is really horrible, but if we were actually looking at which point in particular would be the most accurate, it would be this one, because it's the closest one to the bullseye. Okay? Whereas precision actually has to do with the proximity of how close the various measurements are to each other. So if you look at the example on the right-hand side, which is drawn much better than mine, the reason why, if we look at this example right here, you've got the 3 darts that are in really close proximity to each other, so therefore they have good precision, but they're very far away from the actual bullseye, so they're not very accurate. You can also have 3 darts that are spread all over the place, so it's poor precision, and it's poorly accurate. Or we can have it where all three are in the bullseye, so they both have great accuracy and great precision. Dimensional analysis is perhaps the most important skill that you need to learn right now. And that's the ability to do mathematical measurements and to convert between units and units, okay? So I'm going to try to teach you the way that I learned it and give you some examples of that. Okay, so let's look here at this specific example. The U.S. quarter has a mass of 5.67 grams and is approximately 1.55 millimeters thick. The Washington Monument in Washington, D.C. is 575 feet tall. If you stacked a stack of pennies as tall as a Washington Monument, how much would it weigh in kilograms? They've given you the conversion factor that 1.00 inches is equal to 2.54 centimeters exactly. Okay, first of all, I know you're going to say like that has absolutely no bearing whatsoever in real life. However, this is just to show you how to use the math and use what's called dimensional analysis to go and convert from units to units. So what do we need to know? Well, we have stuff. What information do we have? What do we know? What do we not know? Well, we know mass, and that's what it's asking. But the mass is given to us in grams, and ultimately, we're going to need to know kilograms. So therefore, we're going to need to know how many grams are in a kilogram, or vice versa. We also are giving distances, millimeters, and feet. There's not a direct way to go between millimeters and feet. Okay? The other one is the Old English units, the feet, which are measured in inches. And then the SI units, millimeters. And we're given centimeters. So, let's start off with what we do know. Alright, so let's first determine how tall the Washington Monument is in millimeters. Alright, so we have 575 feet. We can say that 1 foot is equal to 12 inches. 1 inch is equal to 2.54 centimeters. Now, you may know that 1 centimeter has 10 millimeters in it, but let's say that you didn't know that. The way that you can convert that is there are 100 centimeters, because centi means 1/100th for every meter, and that 1 meter has 1,000 millimeters. Okay? So we're just trying to figure out how tall the Washington Monument is in millimeters. Now let's go through and we can check to see if our units all cancel out. You have a feet on the top and a feet on the bottom, so they're going to cancel. An inch and an inch, they're going to cancel. A centimeter and a centimeter will cancel. And a meter and a meter. So the only unit left are millimeters, which is what we're wanting the height to be in. So now let's use our trusty calculator. What you do is you multiply everything on the top and you divide by everything on the bottom. So if you don't want to skip any steps, which right now I'm trying not to skip any steps, we would have 575 times 12 times 2.54 times 1 times 1,000, and you're going to divide by 1, 1, and 1, and by 100. You get this huge number. And at this point in time, I'm not going to worry about significant figures. You only want to worry about significant figures in the very end. So you're going to end up with 175,260 millimeters. Okay? So let's just write that down someplace else. I'm going to have to erase all these strokes. So we want to keep in the side here, we know it's 175,260 millimeters tall. So let's now figure out how many quarters will be in that. We know that for every quarter, so I'm just going to call it Q, is equal to 1.55 millimeters. So how many quarters is that? We also know that we can actually say that 1/4 is equal to 5.67 grams. So let's see how if our units are going to cancel. We have a millimeter on top, millimeter on bottom. We have a quarter on top, a quarter on bottom. The only unit left is grams. Just multiply by everything on the top, divide by everything on the bottom. So if I take 175,260, I times that by 5.67, divide it by 1.55, I'm going to get, and I'm going to write just several of these numbers down, 641,112 grams. But the answer is asking for kilograms. So finally, you just take that 641,112 grams. We have to convert from grams to kilograms. 1 kilogram is equal to 1,000 grams. So this will be 641.112 kilograms. Now we worry about significant figures. So if we go back into our original 5.67, and we're only doing multiplication and division, 5.67 has 3, 1.55 has 3, 5.75 has 3, and both of these numbers have 3. So we need to go to 3 significant figures, which will be 641 kilograms. So that mountain of quarters, or stack of quarters, would be 641 kilograms. I deliberately picked one that was really difficult because in class, what we'll do is we'll also work on some that are less difficult and build our way up to those that are more difficult. Hopefully, this will help. So that's going to end this discussion on dimensional analysis and on the use of significant figures. I'll see you in class.